Good afternoon, everyone. Thank you, Duncan, for the kind words. And yeah, thanks, guys, for joining us. I hope you are having a good time with us. And today I would like to present the work I did as a PhD student here in Bristol, which actually being submitted. I did it with Dr. Pablo. And we would like to talk about application of sensitivity analysis to different hydrology domains. Now, you don't be scared about the next slide. Yes. Okay. So, because if you ask, yes. So this is an hydrology event. Well, I spent 1 year in London at the Institute, and while I was there, I met different people with biology, epidemiology, pharmacology background, and we had all the same issues. Was how can we model our complex reality with mathematical models that have to be easy and simple and help decision making. And one of them worked on this project. Basically, they were helping GPs in submitting drugs to people with high blood pressure, and they have to understand if you have a cut in your vessel, if the high blood pressure causes more blood loss as well. In this model, they basically you have four main different key areas when you have a cut. So basically, you have the blood keeps coming, the platelets are activated, each platelet, many biology and chemist reaction happening around the platelet, and at the same time the platelet is called the unactivated one. And finally enough, you have the clotting process, which is the C, and your cut is pristine. But now, how did they go from approximately 96 random variables to only 9? Well, they use local and regional, they use local and global sensitivity analysis, in this case a variance one. You can tell him, for example, they monitored 3 sensitivity metrics, but sensitivity metrics like the lag time, the relative rate of blood flow, and the final concentration of thrombin, that they could actually measure in situ in the lab. This is an important case in research. But so let me show you how they do that. Well, basically these are the main key steps on sensitivity analysis. You have a certain number of random variables, you assign them a probability distribution. Then your model, mainly the model is a black box model, because it relies on differential equations that we rarely can solve by hand, so we numerically solve them. And it's usually done in a computer. But because these computers are quite encrypted in commercial software, we cannot see the underlying algorithm. So we can see it as a black box model. Then you run this model multiple times to get a probability distribution of model output. But it's not ended there, because you have a probability distribution of a model output, okay? So which you don't know the population of model output. So you are sampled from this population. But how many times do you run your models? Well, it's an unknown. So you have to do by guesses. So and that's why you need a convergence study. For example, for a study that I did last year, I needed 100,000 simulations, and I did the convergence assessment, because what you basically have, your model output, the flow discharge that you are simulating with least flow. You have the sample mean and the sample variance, and what you have to assess by bootstrapping is that your sample mean and sample variance are constant as long as you increase the number of multiple runs. Only once you have the convergence study, well, you can use the results of a model output. And you can use for two different things. For the uncertainty analysis, well, you can estimate your mean distribution, okay, on model output, and provide a confidence band, usually 95%, or for sensitivity analysis. In our case with Pablo, why we use it? For reducing the number of variables to survey on site, right? So let me present a bit of more literature review what we did. So basically, what you can have you need to define the scope of your sensitivity analysis. Based on that, if you are interested on the derivatives of your model output, well, go for a local sensitivity analysis, and you can vary each random variable at once. But if you're searching for other things right? How do the variables affect your function, or how do how the interaction affect your model output? Well, you have to abandon the local level, and you have to go for the global type of sensitivity analysis. Now, which kind of global sensitivity analysis depends on the number of model runs you need, and again on the scope of your analysis. In our case, we did regional sensitivity analysis, and we were all at a time fashion. What does it mean? We had 11 random variables, and we varied 11 random variables all together. So which made everything tricky to understand. When the software wasn't working, made everything a bit trickier. Now, we saw how to vary, we saw the type of analysis, we saw how we vary the random variables, we saw how do we do the convergence study. We need to understand how many times do we have to run this software, because we don't know it a priori, right? What people do, let's say, oh, I do 1 million simulation, but you cannot wait 1 year, right? Because at least in civil engineering, when they give you a job, they want it done for the day before. So, So what you can do, you can go to the literature review. Now, unfortunately, I have to say, this is a critic to a lot of scientific research. Many people they just don't publish the convergence study. So what you have to rely on what you have. So if you don't have a convergence study for your typical application, so a few studies published, let's say when they reach convergence for different types of sensitivity analysis. In this plot, you can tell that the number of simulation depends on the type of sensitivity analysis, if you go for a regional one, and on the number of model parameters. In our case, we had 11 uncorrelated random variables, all normally distributed because they were physical properties like temperature. The temperature cannot be, or the gravity. They have to be positive numbers. So usually we model with a log-normal distribution. Anyway, so we had 11. You ended this plot. We had 11 random variables, and we needed from 10 to the power of 4 simulation or more. We went to 16 because we reached a good time with basically we needed 4 days for completing 16,000 simulation, which was a reasonable time. Now again, the last point before starting the application is you have to generate your random numbers. Now you can imagine there are many methods around how to generate these random numbers. Me and Pablo, what we did was we applied a quasi-random subord because we also use our results not just for doing scatter plots and parallel plots, but because also there is another method of global sensitivity analysis, which is the subord one, and which basically you have the variance of your model output. What you want to map how all the random variables contribute to the variance of model output. That's why we use the subord. And you can also tell that all different, I would recommend, in your application, I quite recommend to use this quasi-sampling method because they better fill the sample space. You can tell that a crude Monte Carlo needs more samples. In this case, we plotted 250 points. And now now we saw how do we analyze results. Well, this is quite tricky. What we suggest is to having a dashboard of all data visualization tools. Because, for example, you have the variable x2. If you only look at the parallel plots, you will have that the variable varies between 0 and 1. So someone could say, oh, it's not meaningful. No, because if you look at the scatter plot, you have an exponential relation, even though that sensitivity index is small. So what we suggest is always, data can lie to you. So not just rely on one data visualization tool. And now we can pass to Pablo, which we did our first application.
Thank you, Giuseppe. Hi, everyone. Well, now we'll show you the first application of the sensitivity analysis method. And basically, one of the applications is for the assessment of hydrological hazard interactions. And to understand a bit more, hydrological hazard related to landslides, debris flow, erosion, flash flood, basically related to hydrology and triggered by rainfall in this case. And by interaction, it means by the interrelationship between hydrological and stability processes that influence the interaction between these hazards. So basically, one of the applications of the global sensitivity analysis method is because allows the exploration of the input parameter space. It's basically to assess the interaction between hydrological hazard. We need to use a multi-hazard model, specifically spatially distributed models, which are quite complex. They need lots of input parameters. So specifically in data port context, where there is no much data available to estimate these input parameters, the global sensitivity analysis approach offers a possibility to explore different input parameter range. Also, it quantifies the relative importance of each input parameters, specifically ranking, mapping the most important parameters inputs, helps to prioritize resources and focus on the most influential inputs. For example, helps to improve data in data port context, allows the evaluation of uncertainty and identification of parameter set values that best represent hazards in this case, and also allows the more or less to select input parameters that will reduce uncertainty in hazard representation. However, when we use multi-hazard models specifically to assess hydrological hazards, there's some considerations that we need to basically consider in this case. The large number of input parameters, for example, the more combinations of input parameter values, the greater the number of evaluations, for example, longer simulations time when we use high resolution images or data, and that especially in large catchments, so they are computationally expensive in this case. So basically, one of the applications was in St. Lucia, it's a Caribbean, in the Sophia catchment, where in 2010 Hurricane Thomas were in the area, basically. And in that case, basically within the Sophia catchment, there were multiple hazards, specifically hydrological hazards. And considering the application of global sensitivity analysis, specifically by using multi-hazard models, there's some other considerations. Well, that catchment, there is not enough data. We use spatially distributed data. We are using complex model, multi-hazard model, basically. And that basically introduced lots of data uncertainty, also considering model uncertainty. So basically, epistemic uncertainties are introduced in the hazard representation. So before the application of our global sensitivity analysis and the use of complex model, we need to use or follow better practices. And this is basically a methodological step to use complex model, basically, and to assess and to apply global sensitivity analysis methods. So within the use of the following the better practices, I introduce a workflow, basically, which is an assembly of parametric simulations, by the use of global sensitivity analysis method to explore different parameter set combinations with different value ranges. There is another process, which is the model verification, in which we select a parameter set combination that best represent the hazard representation. Basically, the model verification is based in hazard observations, and then once you select the parameter set, you can apply a regional sensitivity analysis to assess which is most important input parameters within the parameter set and affect the hazard representations. So basically, following the workflow, I'm going to, different parameter set values were selected according to land use and soil type categories. It was identified the input value parameters, basically the range, the distribution of those parameters. We explore different parameter set combinations, basically by increasing or decreasing this parameter range. Parametric simulations were performed using global sensitivity analysis. Then model verification was performed by selecting the suitable parameter set that best represent hazard representation. And then the regional sensitivity analysis was applied to identify which were the most influential parameters. The results, well, 144 simulations were performed. Simulation 22 was selected as the best represented the hazard representation in this case. The application of the regional sensitivity analysis identified, for example, in this case, saturated dry conductivity, moisture content, internal friction angle as the most influential parameters. So basically, once you identify the input parameters, you can identify how these values are distributed for different land use categories or soil types. And basically, one of the final considerations by using global sensitivity analysis, using complex model is the time of simulation, their computation is expensive. You can identify key parameters into parameters that influence hazard representation, and also basically to improve data, basically. And by identifying the most simple parameters, data can be improved, reduce the impact of uncertainty, and basically, well, that's it. So just to finish.
Yeah, just, do we have time? No, no, yeah. Yeah. No, it was just, we also did a second application, just, do a bit of scatter plots and give you a bit of, some practical, how to estimate the probability, and all that we saw. We actually use the dashboard of scatter plots, empirical cumulative distribution function, but for a problem of 11 random variables like ours, we had 4 kind of plots. Basically, we ended up with 96 plots to investigate. So it was quite, So and this was a bit of research ethics, guys. So I would like to say, like Conan Doyle says, it's a capital mistake to theorize before one has data. Insensibly, one begins to use facts to suit theories instead of theories to suit facts. I hope we increase the discussion about these things and ask you to honestly ask to journalists, I want to see the digital model, I want to see the data, I want to analyze the data by myself with my knowledge, with what I know. Okay, thanks guys. Thank you.